Good morning, students. Welcome back to another session on problems on design of tension members from steel structures subject. So in the previous class we have discussed regarding the design of tension members, different forms of tension members, applications of tension members, and we have seen some design strength formulas with respect to cross section yielding, net section rupture, and block shear, and we have solved 3 problems also. Later on we discussed regarding the what are the different types of problems in a tension members. So coming to here again, once again I will revise this small topic: analysis and design problems. What is the difference between analysis and design problems? Suppose if the sectional details are given, sectional details like whatever it may be, angle section or eye section or channel section, whatever it may be, if the section details like ISA, Indian Standard Angle, either it may be equal or unequal, means here see 200 by 100 by 15 mm is given, means this is unequal angle section. Okay, to this section you are supposed to calculate its strength. How you will be calculating? You will be determining the design strength due to cross section yielding TGD and net section rupture TDN and block shear TDB. Okay, from these 3 the lesser value you obtain will be the design strength of this particular section given. This is the analysis. Coming to the design problem, okay, here certain load will be given. Now to that load, okay, you factor it. If it is a only load, you have to multiply with 1.5, you will be getting the factored load. To this factored load you have to choose the section. Now for choosing the section you have to assume this value. What is this value? Tensile stress, design permissible design tensile stress. Okay, if it is denoted by generally FTD. Okay, permissible design tensile stress. F is denoted by stress, T is nothing but tensile. Okay, so that value will be assumed by taking the factored load divided by that stress. You will be getting the area. Okay, to that area you add 10%, means you take excess of 10% of area, means 1.1 you have to multiply with the value you got here. Okay, so you will be getting some area. Based upon that area, from the steel table you have to choose the section. Okay, after getting the section, the process will be same as that we done in this one, means calculating its design strength due to cross section yielding, net section rupture and block shear. In that same, the lesser value will be its strength. That strength obtained should be greater than this value, then only we can say that our section which is chosen, okay, is perfect, means it won't fail. Is it okay? These are the 2 different problems you are going to do in these tension members. Not only in tension members, in every chapter involved, and even in design of RCC, reinforced concrete structures also, you are going to do the same analysis and design. While doing the design problem, certain values should be assumed as per code, as per here as per IS 800 2007, and in your RCS as per IS 456 2000, you will be having different design aids. Based upon those design aids, you are supposed to assume particular value and you have to obtain the value. That value should be checked with the value or load whatever it has been given. If the load obtained here is excess more than this one, then our design is perfect. Okay, now we'll solve one more analysis problem, then we'll move to the design problems. Okay, so in this analysis problem we'll be having single angle section, double angle section, right? We'll be seeing today. Okay, so you can note down this question. Determine, okay, the design tensile strength. Determine the design tensile strength of ISA 150 by 75 by 10 mm. Okay, connected to the gusset plate, by 6 mm fillet welds. Okay, the length of weld is 300 mm. Take Fi as 250 Newton per mm square and Fu as 410 Newton per mm square. So this is the value. Okay, now it is connected to a gusset plate. Okay, 150 by 75. This is 150 and this is 75, and the thickness is how much? It is 10 mm. It is welded here. It is welded here. This is the question, and I will write the length of weld LWR LC, connection length, right? 300 mm. Okay, Fy is 250 Newton per mm square, Fu as 410 Newton per mm square, and angle section ISA 150 by 75 by 10 mm. Okay, so first we'll see design strength due to yielding of gross section. How it is denoted? TDG. Okay, now what is the formula as per IS 800/2007 clause number 6.2? TDG equals to AGFY by gamma m naught. Okay, now Fy is there, gamma m naught for yielding it is how much? 1.10. Okay, now Ag for a given section you can calculate here easily if it is steel table is not available at present. So 150 minus of 10 by 2 into 10 plus 75 minus 10 by 2 into 10. So how much it will be? It will be 10 by 2 means 5, 145 into 10 means 1450. Okay, plus 75 minus 10 by 2 means 70 into 10, 700. So total it will be around 2150 mm square. Okay, so this is the area obtained. Now substitute here in this formula. So 2150 into 250 divided by 1.10. Okay, 2150 into 250 divided by how much you are getting? 488.363 into 10 power 3 newtons. Okay, so this is the value design tensile strength due to cross section yielding. Okay, next second we'll see design strength due to rupture of net section or critical section, whatever it may be, both will be called. Okay, so for that, what is the formula as per same IS 800 2007? TDN equals to 0.9 ANC FU by, okay, gamma M1 plus beta AGO Fy by gamma M0. Now first ANC, area of net area of connected leg. What is the net area of connected leg? 150 minus 10 by 2 into 10, so 1450 mm square. AGO, gross area of outstanding leg, right? So AGO 75 minus 10 by 2 into 10. Okay, so it will be around 700 mm square. Next, what is the beta formula? Beta equals to 1.4 minus of 0.076 into W by T into Fy by Fu. Okay, if it is remembered, it is well and good. If not, it is available in a code. Okay, clause 6.3.3, it will be talking about all these things, right? Now what is W here? Outstanding leg length. How much it is? 75 mm. Similarly, for a welded joint, BS will also be equals to 75. Next, length of weld LC is given as 300 mm. Fy, Fu, everything is the thickness is 15 mm. If I substitute here B for beta value, 1.4 minus 0.076 into what is W? 75 by thickness is how much? 10 mm. Okay, into Fy 250 by Fu 410. Already these are given data, right? Into 75 by 300. Okay, if I solve this one, 75 by 300 into 250 by 410 into 75 divided by 10, this value, okay, deduct from 1.4. How much are getting? 1.313. Okay, beta minimum is how much? 0.7. What is beta maximum? Okay, Fy gamma M0 by Fu gamma M0 by Fy gamma M1. Okay, so how much it is? 410 into M0 is 1.1 divided by 250 into 1.25. Okay, so 410 into 1.1 divided by 250 into 1.25, so 1.44. This is maximum, this is minimum, it is in between. So beta value is equals to 1.313, which is less than 1.44, and it is greater than 0.7, hence it is within the limits. Okay, now if I substitute these all values here, TDN equals to 0.9 into what is ANC? 1450 into 410 divided by, it is 1.25 plus what is beta B? 1.313 into 700 AGO into Fy is how much? 250 divided by 1.10. Okay, so if I substitute here 0.9 into 1450 into 410 divided by how much it is? 428.04 into 10 power 3, only this value, plus 1.313 beta value into 700 AGO into 250 divided by 1.10. Okay, so how much you are getting? 208.88 into 10 power 3. If I add all these things, 428.04 plus 208.88, so how much you are getting? 636.92 into 10 power 3 newtons. Okay, what is this? This is the value for net section rupture. Okay, next we'll see third one, design strength due to block shear. Okay, now here what are the two formulas? TDB1 next to TDB2. TDB1 is what? AVG, okay, Fy by root 3 into gamma m naught plus 0.9 ATN Fu by gamma m1. This is one formula. Another one is what? 0.9 AVN Fu by, okay, root 3 into gamma m1 plus ATG Fy by gamma m naught. Okay, now what is this V indicates? This V indicates shear and T indicates tension. Means AVG or AVN is nothing but what? Area under shear. Now how to calculate this? Means two sides will be there, okay, that is length of weld into 2 times into thickness. Means if I connect like this, this one, okay, this is area under shear and this is area under tension. So 300 into 2 into thickness of plate is, so how much it is? It is 6000 2 3 to the 600 into 10, 6000 mm square. Next ATN, okay, length of connected leg into thickness. This is the connected leg, into thickness. How much it is? 150 into 10. This is the areas under shear and area under tension. Okay, now first we'll solve TDB1, right? TDB1 I will substitute here directly. AVG is more 6000 into Fy 250 divided by root 3 into gamma m naught, it is 1.1 plus 0.9 into ATG area under tension 1500 into 410 divided by 1.25. If I solve it separately, 6000 into 250 divided by root 3 into 1.10, how much I am getting? 787.29 into 10 power 3 plus 0.9 into 1500 410 divided by 1.25. So 442.8 into 10 power 3, 787.29 plus 442.8. So okay, 1230 into 10 power 3 newtons. This is TDB1. Next, TDB2, 0.9 into 6000 into, okay, 410 divided by root 3 into 1.25 plus, what is it? 1500 into 250 divided by 1.10. Okay, if I solve it, 0.9 into 6000 into 410 divided by root 3 into 1.25. So how much you are getting? 1022 into 0.60 into 10 power 3 newtons plus 1500 into 250 divided by, so how much you are getting? 340.90 into 10 power 3. Overall you are getting 1022.60 plus 340.90. okay, so how much it is? Around 1363.5 into 10 power 3 newtons. Okay, now these are the values you obtained. Now what is the design strength of tension member ISA 150 by 75 by 10 mm means lesser of the above three values. Now from here, TDB1, TD2, which is less than this one, so this one to be chosen. Next, TDG, TDN and TDB. What is TDB? 1230 into 10 power 3 newtons. What is this one? Okay, next, what is AG? Okay, 488.63 kilon into 10 power 3 newtons. Okay, so out of these three values, which one is lesser? This value, TDG. Okay, so design tensile strength of ISA 150 by 75 by 10 mm is how much? 488.63 into 10 power 3 newtons. Okay, this is the design strength of value we can obtain for the given section. Okay, so we'll see the next problem. So this is the problem. Next problem, determine the design tensile strength of a roof truss member consisting of two ISA 80 by 50 by 8 mm connected to both sides of gusset plate of 12 mm thick. Okay, connected to gusset plate of 12 mm thick with their longer legs by 4 mm size fillet weld, LC 250 mm, FU 410 and FI 250 mm. Okay, so this is the gusset plate. To this gusset plate, okay, either side of gusset plate they have connected two angle sections. This is 50 mm, this is 80 mm. Okay, what is the given data? FY 250 MPa, FU 410 MPa and LC 250 mm, and the angle section is 80 by 50 by 8 mm. Okay, so first, design strength. Due to yielding of gross section. Okay, yielding of a gross section. So for that formula you already know, that is TDG equals to AGFY by gamma m naught. Now if you want to take the area of double angle section, in steel table it is not available directly, so each angle area you have to calculate and you make it into 2, that's all. Okay, so AG, if steel table is not available, this is the procedure: 80 minus 8 by 2 into 8 plus 50 minus 8 by 2 into 8. How much you are getting? 74 into 8, 76 into 8, 76 into 8 plus 46 into 8. So you are getting around 976 mm square for each angle. Okay, now for double angles, two into 976. So how much it will be? 1952. It's 1952 mm square. Now TDG equals to 1952 into 250 divided by 1.10. This is constant yielding, right? So into 250 divided, so 443.63 kilonewtons. Okay, next, design strength due to rupture of critical section. So what is this? TDN equals to 0.9 ANCFU by gamma m1 plus beta AGO FI by gamma m naught. Okay, now what is ANC? Connected leg length. So 80 minus 8 by 2 into 8, you will be getting around 76 into 8, 608 mm square. Next, AGO, outstanding leg, 50 minus 8 by 2 into 8. Okay, so 46 into 8, 368 mm square. Now beta you have to calculate, right? So for beta, what is our formula? 1.4 minus 0.076 into W by T into Fy by Fu into Bs by Lc. Now 1.4 minus 0.076, what is W? This one. Okay, 50, thickness of plate 8 into Fy, how much it is? 250 divided by 410 into 50 divided by What is the length of L given? 250. So if I solve this one, 50 divided by 8 into so beta value, how much you got? 1.34. What is beta minimum? 0.7. Beta max already we calculated in the previous problem. It is 1.443. So beta value is it between. Okay. Now substitute here. 0.9 connected leg area 608. But 2 right, double angle, so into 2 into 410 divided by 1.25 plus. Okay, so beta is 1.34 into what is the area? 368 into 2 into fy 250 divided by 1.10. So 0.9 into 608 into 2 into 410 divided by 1.25. So 358.9 kilonewtons plus 1.342 into 368 into 2 into 250 divided by 1.10. So 224.48 kilonewtons. Altogether, how much it is? This is the value you got for what? Design strength due to critical rupture critical section. Next, design strength due to block shear, that is TDNB. So TDB1, TDB2. What is TDB1? AVG Fy by root 3 into gamma m naught plus 0.9 ATN Fu by gamma m1. And what is the formula for this one? 0.9 into AVN Fu by root 3 into gamma m1 plus ATG Fy by gamma m0. Okay, this is the formula. Now what is AVG? Area under shear, that is LW into 2 into T, two sides 2. So 250 into 2 into 8 into 2. Okay, 32 into 250. How much you are getting? 250 into 2 into 8 into 2. Next, ATG. Okay, 2 times of length of connected leg into T. So 2 into 80 into 8. mm square. Okay, now I will try to substitute here. TDB1 already we doubled it, no need to write again 2, okay, into 250 divided by 1049.7 kilonewtons. This is 1472.5 kilonewtons. Okay, next with respect to second one, TDB2 0.9 into 8000 into 410 divided by √3 into 1.25 plus 1280 into 250 divided by, what is gamma m naught? It is 1.10. $1363.4 kilonewtons plus this one 1280 into 250 so 290.90 kilonewtons. Now you got 4 values. Here it is 1427, this is 1654. So in design strength due to block shear, TDB1, TDB2, this is the least value, and overall from TDG, okay, next TDN and TDB. What is TDG? For 43.63 kilonewtons, and TDN it is 583.38 kilonewtons, and it is 1427.5 kilonewtons. Okay, so out of these three, the design tensile strength is what? This one, 443.63. okay, so I hope you understood these two problems. In the next session, we'll try to start design problems, design of tensile strength. So earlier I discussed design means load will be given, for that you have to decide the section, okay, and here we have seen two problems today, that is analysis for a single angle section, okay, and analysis for a double angle section. The only difference between these two is, while taking the gross areas or area, average shear areas like that, you have to take it double. See here, instead of AG they will be taking only one, this value, but here because of being double you have taken into 2. Similarly here also you calculated the area as singles, but while multiplying you have done with 2. In this block shear also, while calculating itself we have multiplied separately with 2, because two angles are connected. Okay, thank you.